Hello everybody, my name is Marianne. I became a faculty member here 3 years ago. It's my third year. And I've been hired as the first experimentalist in astrophysics in the department. So I'm doing observational astrophysics, which means I'm using very large telescopes to observe the universe, and I do all kinds of big data analysis on the data we receive from the telescopes to do all kinds of analysis. And so my main medium of work is actually the light we receive from the universe, which is what we're going to talk about throughout the course, right? Electromagnetic waves, lights, etc. Tell me if there is something that is not clear English-wise, okay? Just feel free to ask questions and stop me. I didn't do my studies in Israel, so it might be felt at some levels, and this is another opportunity to encourage you to ask questions if some of the notations are different from what you're used to, etc., etc. Okay, so in this course you will realize soon enough that there is a lot of repetitions from things you've studied already. In optics, in electricity. Okay, you're going to hear again things that you've already heard. I think from what I understood from you from previous years, you're going to hear it from a slightly different perspective, in a slightly different way. And this aspect of the course, the repetitive aspects, should really not make you feel that it's going to be easy, okay? Every year we are surprised by every year we get this feedback that students feel that we are repeating things they have studied already, and we're always surprised by the grades in the final exams, okay? So I'm not saying this to discourage you at all, the opposite. I'm telling you, enjoy the parts that are repetitive and use them as a way to refresh things and to feel more comfortable with the more technical parts, which I think will be new, okay? And the parts that are repetitive should be an opportunity to solidify the foundations that you already have, okay? This is one thing. The Moodle will be updated today or tomorrow, okay? We had a small delay in the start of the course. Are there some Milwimnikim, do you know, in this year? Do you have fellows that are in Milwim?
אני אחראית על קבוצה ונכנס כרגע סטודנט אחד.
הקבוצה של המילואימניקים? Okay, so I'm a wife of a Milwimnik, and this aspect has very much influenced my experience this year. So this too is something you should really feel free to share and come, and if the Milwimnikim have any issue, it's something that I'm very well aware of and very keen to help with, okay? Okay, this brings me to the way we're going to interact. It's a very big course. I think there are 100 registered students, because we also have engineers and physicists, okay? And from previous years, we've learned some lessons, so we're being very square in the way communication is working in this course. Everything which is related to the logistic of the course, for example, we're going to have one completion course during the short מחלקה, because of the course we missed. All the logistics will be communicated through the two מתרגלים who you haven't met yet. Okay, Jonathan and Tomer, they are very nice people. All the logistical things go through them. All the things that are more personal, okay, personal issues that have prevented you from doing X and Y, you can share with me via email, okay? No use of my personal number, in no way, okay? But email, I don't answer very quickly, but I always answer, okay? But so for all the things that are more personal, I welcome you to talk with me, and for the more logistical things, talk with the tutors, just because otherwise it falls בין הכיסאות, okay? Because there are so many people, and okay? So this is the best way with fun. And until next time, we need you to choose 2 representatives, okay? And if you don't choose them, I will have to choose them. So please, by next week, choose 2 people who will be our contact people, or okay, if and the reason we are doing this is because in the past there have been some requests which we thought were representative of everybody, okay, regarding grades, regarding the pace of the course, etc. And then we made some changes, and then we realized that it wasn't representative at all. So then it became too fast, etc., etc. So we don't want this to happen again. So we need 2 people that you all agree represent you, and if they come with requests, we can be sure enough that that they are talking in your name. Okay? Everything makes sense. Okay. The grade composition. So it will be the following. There will be homework. Homeworks every week. We will not check all of them, okay? We will pick some, and this will be 5%, 5 points. Okay, you get 5 points if you handle the homework every week. Okay, then there will be 2 exams, מבחנים, which will be מגנים. How to say מגן in English?
What will you grade?
I mean, they can only improve your grade, okay? It means that if you have 0, it will not count. If they somehow improve your grade, they will be counted, okay? They will count as 15% of the grade, and they will be almost 1 by 1 exercises taken from the homework. Not 1 by 1. They will be very inspired by the exercises that you will receive in the homework. Last year we did it 1 by 1. We decided that we should improve this. 1 second. So, okay, so if you do the homework, if you understand the corrections that you give, etc., you should get these 15 points as presents too.
Each exam
איך
is
קוראים לך?
Rom.
רום.
Each exam is 15%?
No. Together they are 15%. Okay? And then, thanks for asking. And then the final exam will be 18%. Okay? But these 2 things, you should really understand that they come together. Okay? If you're studying the exercises of the homeworks and the solutions we give, you should get these 20 points for free. Okay, and the goal here is to help you keep track and not lose track during the semester. Okay, and just do the homework. Okay. Okay. The dates will be given on the Moodle in the next 2 days. This I did. The representative we talked. Okay, there will be, and these, all these exams, for all these exams you will have דף נוסחאות, a formula sheet, okay, which will be from last year. If there is something very important that you would like to add, of course we will add them, but there is one thing which will not be in any formula sheet, which is the Maxwell equations. This is one of the principles of this course. We want you, by the end of this course, to know the Maxwell equations in all the different shapes and styles, by heart, even if we wake you up in the middle of the night. Okay, it's 4 equations, and we deeply believe that in order to say that you have a BA in physics, you need to know them by heart. So this is one thing that will not be on any formula sheet, and you will have to know it by heart if you don't already know it. Okay. If someone wants to type some notes, we are also open to add some bonus for this. Okay. If some of you volunteer to type notes of the course, so that we have a nice book note at the end, we will give them additional points. And and the last thing I want to say is that this course, among other courses that you have during this semester, is one of the last pillars of your studies for a BA in physics. Okay, the equivalent course exists in many different universities in the world. It's a very classical one, very fundamental one, and in a sense, it's going to, we'll see it in the rest of the lecture, but it's, if you think about it, electromagnetism, okay, let's put it differently. If we think about our everyday experience of the world, okay, what are the things of physics that we feel the most? Okay, your experience as a human being, what are the physical phenomena that you feel the most? Okay, so light, but like gravity, okay, so classical mechanics give you one of the pillars of your everyday experience. And the other thing is light, okay, everything we see, everything that we're surrounded, that the world that we see which surrounds us is only visible because of electromagnetism. And you will see the Maxwell equations were formulated and discovered pretty recently, okay, maybe a bit more than 100 years. And so we should feel very fortunate that we are being given these equations, these formulations on מגש כסף, plate, okay, and we should feel very fortunate that we're lucky enough to study physics when the number 1 or number 2 component of our everyday experience has been formulated in a very clean way and is very well understood, and this actually opens the understanding of a major part of our everyday experience as human beings. Okay, so this was the introduction. Are there any questions on the administrative, logistical things? Okay, the שעות מחלקה, we can assume that are open for completing courses, right? Yes, okay. So let's start, yes?
Is there a book for the course?
Ah, yes. So this is the book that the lecture is the most inspired from, and many of the exercises that we will give are taken just from this book. Okay, it's called Introduction to Electrodynamics by Griffiths. It's a classic Griffiths, and it's in the library. Okay. Griffiths. And very often I will tell you, this is being described in more details in the Griffiths, etc. Okay, so I really encourage you to look at this book, Introduction to Electrodynamics. Okay. Yes, thanks for asking this. יש לנו מזגן, מתפוצצת מחום. מישהו יודע להפעיל את זה? אז מישהו מתנדב? אתם בסדר? נדליק טיפה? טוב, יופי. Okay, so today we will touch upon 2 things, okay? I will start with an introductory chapter, which is a reminder of many things that I think you already know, but we really need them in this course, so vector analysis, things like this. So this will be one part of the course, and the other part we will start to talk about stationary system and electrostatics. I can raise this. And in terms of the structure of the lecture, I will talk for 1.5 hours, then we will have half an hour break, and then another 40 minutes. Okay? So, chapter 1, introduction. Okay? Okay, and so one thing we will start with is vector analysis. Okay? And we will start with the operators, which you already know, but the goal now is to refresh things, okay? So we'll start with the gradient operator. Okay, and for each of the operators I will talk about, I will remind very quickly what's the input, what's the output. Okay, so if we picture this operator as a box, let's remind ourselves what is going in and what is going out. So is this a vector or a scalar? It's a scalar. And what is going out? A vector, which we will write either grad grad A, or sometimes we use the nabla symbol, okay? And let's remind ourselves the formula for them for example, in Cartesian coordinates. So nabla A is dxa, dya, dza, right? Let's remind ourselves the cylindrical. So what do we have here? Because it's a repetition from things you know, I'm expecting some so dr, right? Do you remember here? What's the next one? 1 over r d theta and dz, and then in spherical we have dr, 1 over r d theta and 1 over r sin theta d phi. Okay, I'm not going to do this for all the operators, but this is the basic one. Okay, the second one is the divergence operator. So let's remind ourselves what's going in and what's going out. What do I have here? A vector. Okay, and here I'm getting what? A scalar. Okay. And in Cartesian, div of A is dxax plus dyay plus dzaz. Okay, I'm not going to remind the other coordinates one, but remind yourself of them, okay? And in terms of the intuition, what does the divergence operator actually tells us about a vector? Do you remember what do I learn from the divergence in a given point? Okay, so I'm hearing flux. What else? And I was thinking more the divergence in a point, what information does it give me?
If it flows in or flows out.
Yes, okay, so it gives me an information of the flowing in and out, but not exactly. So let's so the divergence is actually telling me how much a vector is describing a movement of divergence, okay? How much things are spreading from a certain point. And there is a metaphor if you put some dust on water, okay, or some sand on water, and then you look at what the dust is doing. And in the case, in this example, the vector is actually the velocity vector fields on the water, okay? So the dust or the sand is tracing the velocity vector, okay? And so I will show you several cases and you'll tell me is the divergence positive, negative or null, okay? So basically a sink, somewhere which is a sink will have a negative divergence. A place which is a source will have a positive divergence, but let's give examples, okay? So if I have something like this, and I'm asking what's the divergence here, it will be positive, okay? But now I'm going to give some more tricky examples. So okay, and here, so here the length of the vector is proportional to its value, okay? So in these two situations, the vector is going in one direction, okay? So what about this, the divergence in this point? Is it positive or negative?
Positive.
Positive? Everybody agrees? Okay, so it's indeed positive, we'll see in a second why, and in this case,
No.
Zero.
here in null,
מה ההבדל? כי זה...
פה,
כאילו
here,
אין שינוי בחלק הזה.
here it's constant, here it's not, okay, and here it's 0. Okay, and the way to see it is to imagine a box, okay, and to ask, is everything which is going inside the box already also going out, okay? So the divergence is telling me something about the difference between what's coming in and what's coming out. Okay, and this is in essence what the divergence theorem is telling me. Okay, so it's called the Green theorem or the divergence theorem. It has all kinds of names and was first discovered by Lagrange in 1762. Then it was discovered independently, but imagine, like, it was a time when communication in the world was such that people could discover things independently with 50 years time delays. Okay, so it was rediscovered by Gauss and Green, and it was demonstrated for the first time by an Ukrainian physicist called Ostrogradsky. And the theorem is telling us the following. So the divergence, this is I have volume V, okay? And so the divergence of A, this is d tau, okay? Tau is a small element of volume, is equal to what? To the flux of n through the closed surface. And this small vector, this is a unitary vector, which is oriented inward or outward? Right. It's oriented outward from the surface. Okay? So this is a very important theorem. Again, in essence, it tells us this. Okay, it links the divergence to summary of what's going in and what's going out, and this allows us to define a conservative flux. conservative flux, okay, which is not a conservative field. I will come back in a second to what I mean by a conservative field. So what is a conservative flux? When do we say that a vector has a conservative flux? If for every closed surface S, the flux through this surface, is 0. Okay, so if for every surface that I define everything that's going in is also what's going out, then I can say that I have a conservative flux. Okay, not to be confused with the conservative field. Okay, and this means that I have a conservative flux, and it also means that the divergence of this field is 0. Okay, surface is 0, and this is equivalent to saying that the divergence is 0 because of the Green theorem. Okay? Okay, so for each operator, I'm actually reminding the basics, giving you a theorem and giving you a definition. Okay, so here the theorem was the Green theorem, the definition was the conservative flux. Let's do the same with the curl operator. Okay, so here again, what comes in, what comes out. Second, what שלך?
אריאל.
Yeah, I will try to remember names from Ariel. Okay, so what comes in? A vector. What comes out? A vector 2. Okay. And in Cartesian again, I have that rho of A is equal to dx, dy, dz. So the product, I will be writing it either like this or like this. Okay? In these two ways. Y and z. Okay? And here again, let's remind ourselves what it means intuitively. So the divergence was describing how much the field is spreading away, diverging from a certain point. Okay, and the rho, it quantifies what? Okay, turbulence is a very broad definition. It defines how much it swirls again a point, okay? How much it rotates, things are rotating again. Okay, how much the field is swirling around the point. Okay, and the way to imagine it, to conceptualize this, is by imagining a small wheel. Okay, so I'll give you an example again. I'll give you two examples. Who said turbulence? What?
Ariel.
Ariel. We have two Ariels. Ariel? Okay, so in this case, in each of these cases, you see, I don't have any rotation here, okay? I don't have any circular shape or anything, but the way to imagine things is like by making here a small wheel, and asking, let's say this is water, are things going to rotate because of the field? Okay, so in this case, no. Okay, so in this case the vote is null, and in this case it will, right? It will make the, so here it's not null. Okay, and here too we have a very important theorem. Can you remind me of the name of it? The Stokes theorem.
רק ביקשו שאנשים עמית לא לעבור את החצים האדומים
אז עברתי?
בצד השני.
אוקיי, בסדר, אני אעשה מאמץ. Okay, so I have the Stokes theorem, which is also called the Curls theorem. C-O-M. Okay, and this reminds me what it's saying in essence.
יש לי שאלה אחרת, היא לא קשורה לנושא הזה, המבחן הוא גם באנגלית או שהוא בעברית למי שלא עברית?
אין לי איזושהי דעה עקרונית, אם אתם רוצים שהוא יהיה גם בעברית, אז אנחנו...
ממש נשמח, להקל על החיים.
בסדר.
Like summing all the points in a loop, like the Rosel, is equals to like summing the current along the loop, something like that.
Yes, something like this. So you're right that it actually connects the flux of the curl through a surface and the line integral of the vector along the lines that defines this surface. Okay, so let's write it in mathematical terms. So if I have a surface like this, okay, which here I have a vector n, and the vector n is oriented according to the right-hand rule, okay? Okay, and these are the boundaries of the surface. Okay, so I will call this L like this. These are the boundaries that define the surface. So the line integral of A along the boundaries is equal to the flux of the curl through the surface. D and ds. Okay? So let's write it in words. It's always easier to remember it in words. So the line integral of a vector over a loop. Okay, we say a loop here because we want the boundaries to be closed. Okay, so over a loop is equal to the surface integral of the curl over the enclosed surface. Okay? Now I will now do a small parenthesis I will give a hint to why it's going to be very important in electromagnetism. Okay, I will not go into the details, but when I reach this point, when we talk today about electric fields, I will remind you. Remember when I told you this small parenthesis? This is what I was talking about. So let's give a small parenthesis. What's the name? What's your name?
Elad.
Eh?
Elad.
Elad. I have zero preference language-wise, okay? Just to make it clear. I did this course in Hebrew the last 2 years, and I was asked to do it in English this year, but to make it clear, I don't have any preference, so, okay?
אנחנו נשמח לעברית,
No, I just want to make it clear that it doesn't come from me.
לא רואים את החלק...
כן, כן, הם אמרו לי, אני... בסדר? Okay, so if I have a field, let's call it B, okay? So this is a parenthesis. Okay, if I have a field which can be written as a curl, okay? If a field can be written as a curl, okay? For example, B equal root of A, okay? The flux of this field, okay? The flux of B will only depend on what? It will only depend on the integral of A. Okay? So this is an important thing. The flux of B will be determined by A. Okay? And it's okay to not fully grasp what I'm meaning now, but when I reach this point later in the lesson, I will say, remember, this can be written as a rot. What does it mean? It means something very strong about the flux.
Wait, does that mean that the divergence of the curl would be 0?
This is always true.
Yeah,
The div of rot is 0.
Yeah, I'm saying, but that's the parenthesis is basically equivalent because you're saying it's only dependent on A, which means the surface
it's not
changes. It means the surface changes. I mean, no matter even if the surface changes, it will still be.
Right. I mean, if I can write this, the divergence will be 0. Yeah, I will come back to this later. Okay, and this, you remember I said that for every operator, I'm writing the meaning, a theorem, and the definition. So the definition here is a conservative field, which should remind you things from, what's the name? What's your name? Itai. What is a conservative vector field? Okay, it's a field for which the line integral is path independent. Okay, it doesn't matter which path I'm using. Okay, the line integral between 2 points will be the same. The line integral on the loop will be 0. Okay, this is the meaning of a conservative field. So, if I write it in mathematical language, so if for each C closed, okay, for each line closed, I have that A dl over C is equal to 0. It will be a conservative field. And I'm now going to write 3 sentences which are strictly equivalent, and this too, it's like a brain gymnastics to remind you things you already know, but make sure you understand why they are equivalent. Okay, so the following 3 statements are all equivalent. Okay? So if for every point M in space I I have, okay, I'm writing it again, rot of A is equal to 0. Okay? If I'm saying that A is a conservative field, okay? These two are equivalent, okay? Why? Because of Stokes. Okay? And the last statement, which is very important, which should remind you things from mechanics, okay? I can say in this case, if I have a conservative field, which the line integral is path independent, or if the rot is 0, or if there exists a scalar function f such that what? How is it? Does it remind you something?
The gradient of it.
Right. A is equal to the gradient of f. Okay? This also is equivalent. Okay, so we have many conservative fields where in mechanics. Okay, all the forces where the energy is conserved are basically conservative fields, and because they are conservative, these forces, we can define the potential energy for these forces and write that the force is, like, it doesn't matter if there is a minus, okay, it's only a matter of definition, but we can write for these forces that are derived from a potential energy. Okay? Good. Okay, so this ends point 1, which was just some refreshing remarks about vector analysis. Where is the... Okay, and the second point of this introductory chapter will be the key ingredients in electromagnetism. So let's remind ourselves what are the main ingredients we have in this theory. What are the
Charges.
Okay, so I'm hearing charges. What else? Currents. So I can put charges and currents in the same category. Okay, which is sources. Okay, sources of what? What are these things generating? Fields. Okay, so I can divide the ingredients, the actors of this theory into two main categories, the sources and the fields. Okay, so let's say the key ingredients. Okay, so I have A, the sources, and I have currents and charges. Okay, so let's remind ourselves how we formalize this, how we define these charges and these currents. Okay, we can have charges, we can have a certain quantity of charges in a certain volume V, and these charges can be discrete and they can be better described by a continuum, right? And whether we are in one or the other cases, we will have an integral description or a discrete description. Okay, this is if we translate it into mathematical terms. Just checking the time. Okay. Okay, so let's consider the more general case where we have a volume V and here a small volume d tau around the point. Okay, so this point, I will always notate some random points by M. Okay, M is just a point where I'm asking a question. Okay, what is the value of a field of a charge in a certain point, I will call this point M. Okay, so here I have a charge, a small charge, delta Qm at a certain time t. Okay, and then I can define a volume density at the point M and at the time t, which is what? The limit when d tau go to 0 of what? Exactly. Of delta Q over d tau. Okay, and the total charge in the volume will be the volume integral of rho t d tau. Okay, and I can of course make similar definitions if my situation is better described by a surface. Okay, I have a small surface here, and I will be able to write similarly a surface integral, so sigma m tau ds, or if I have a tile, okay, with the point m here, dl, okay, and qt, so this is surface density, and this will be the linear density. Okay? So these are just definitions and the way we approach these charges. Okay, now let's remind ourselves what is the current density. Okay, this is a slightly less intuitive definition. So when does current appear, basically?
Charges are moving.
What's your name?
Ariel Gam.
Ariel? Oh, sorry. I already have 1, 2, and Ariel? No. Who's the third Ariel? Ah, Ariel.
יש צפיפות זרם כזאת.
חשבתי שנגיד יש צפיפות אריאל. Right. Okay, so we can define the density of current. Okay, so when does current appear? When there is a movement of charge. Okay, so the current appears when movement of charges. Okay, and the current density. So if we have a surface, I'm giving here the definition of the current density, a surface ds around M, okay, which with so at the point M I have a current density J and T, okay, then by definition, okay, this is the definition of the current density, then delta Q over dt, which is also delta I, okay, this is the intensity of the electric current, okay, this is going to be given by J M T ds. Okay, and I'm putting here an X to say that it's going outside. So let's make sometimes drawing is worth 1,000 words. Okay, and so let's assume that I have some movement of charge which are not perpendicular to the surface. Okay, they are in another direction. Okay, so the net movement of charges across the surface will be described by the product of ds and j. Okay? Okay, so this was one of our ingredients, the sources. Then the other ingredients we have is the fields. Okay, and by fields I mean two kinds of fields, electric field and magnetic field. Okay, so in electromagnetism, the sources and the fields, they influence each other all the time. Okay, the sources generate the fields, and then the fields influence the behavior of the source, etc. Okay, these two ingredients are influencing each other virtually. And how do we measure fields? Through what?
Forces, like we multiply the charge and feel the force.
Okay, so Ariel is telling us that we're actually measuring the field by measuring their influence on the charges. Okay, by measuring the force they exert on a certain charge. So I will start with this. So if I have a continuous medium, the small force which a charge will feel will be dividable into an electric force and the magnetic force, right? Okay, and this I can write it in the following way. If I have a small charge element dQE plus dQV cross V. Okay, so this is the link between the way I'm measuring the forces and how they are related to the fields. Okay, if we have a single charge, this will be written in a slightly different way. So in the case of a singular discrete charge, this is the continuous case, and the discrete case. So I have F, which is QE. Okay, this is always very important to remember. The fields are these are fields. Okay, they are defined in a point in space and time. Okay, plus Q V B M T. Okay, so these things are local quantities. Okay, so a few reminders. I had a physics teacher that she kept telling us, make your formula talk. Okay, like translate them. Never just limit yourself to the formula. We need to squeeze out the meaning from them. Okay, so let's remind ourselves, what does this mean? So the electrical force compared to the electric fields, it's always parallel, right? And the magnetic force, it's going to be 0 when the charge moves how? Right, if the charge moves parallel to the B lines, it will be 0. Okay, so 0 when charges move along B, and it will be maximal when the charge moves perpendicularly to B. Okay. Okay, and what this also tells us is that in electromagnetism, when we will try to measure E and B, we will always ask ourselves, how do E and B influence a particle, which we call the test particle, if you remember from electricity? Okay, so there are different status of charges. We have the charges that generate the fields, and we have the test particle, which is the charge that we're asking how is it affected by the fields. Okay, so the test particle, it's important not to confuse it with the sources. Okay, okay, now I will write something that should sound familiar to you, but I'm not sure whether you heard it in this shape with this perspective or not.
What is the symbol before the V?
V? Cross. This is the product. Vector product.
Cross product?
It's also, we can write it like
okay.
V. But in Europe, people learn it like this, and it doesn't matter how much I try, eventually we will be back with this symbol, so, okay, I will try, I promise to try. Okay, so now I will write a claim, and let's see if it reminds you something. Okay, so, the interaction between any two charges, is unaffected. 1F or 2F? 2F. One is unaffected by the presence of others. Okay, so what does it remind you of? You might have heard this or something very similar with the name, superposition principle. Okay, now here there are a few things that should blow our mind. Okay? One thing is to realize that this is not a logical imperative. Okay? The superposition principle is not logical. It's just empirical. Okay? We measured things, we made some measures in physics, and we discovered that this is true. But it doesn't have to be true. Okay? If the forces here were if the Coulomb force was proportional to Q squared, it wouldn't be true. Okay? So this is empirical, and try to think about it. It doesn't have to be this way. It's just empirical, and because if it's true, it's very convenient for us. Why? Because when I have several charges, okay, not test particle, when I have several source charges, I can separate their influence on the test particle. So I can consider separately their influence on the test particle. Okay, so let's write it. Okay, if I have F, which is Q E dot plus Q V B dot. Okay, and let's assume that these two fields were generated by two sources, Q1 and Q2. Okay, because of the superposition principle, I can separate this and write that this is equal to the force of Q1 on Q plus the force of Q2 on Q separately. Okay, so I can write this as Q E1 plus V cross B1 plus Q E2 plus V cross B2. Okay, and what the superposition principle means here is that I don't have any cross term.
You missed cross product between the B dot and the V.
Okay, so it's this plus this without any cross term, without something of Q1 or Q2 or something. Okay, no cross terms. But it's important to remember that this doesn't have to be. Okay, it's not logical. It's just empirical. And in a sense, it also means that the test particle doesn't know or doesn't care how many sources are generating the fields that it fills. Okay? It doesn't fill whether the field is generated by one particle or by 1,000 particles. Okay? And the influence it fills is the same as if there was only one. Okay, so this was point 2. Let's see, 20 minutes. Okay, so third thing I want to go over are the superstars of this course, the Maxwell equations. So it's important to know that Maxwell actually never formulated them. Maxwell equations. They basically emerged from his theory. Okay, he did formulate all kind of other things, and the equations are theirs. But he didn't write them like in this way. It's Hertz and a British physicist called Heaviside who basically formulated them, and the current formulation, which I will write now, is the formulation by Feynman, Richard Feynman. Highly recommended to read all his books. Okay, so the first thing in the Maxwell equations is this. For each point in space and every time in the time. Okay, this is true everywhere, every when. Okay? For each point in time and space, we have 4 equations.
What is it?
Let's see. M is a point in space. M, it will always be the way I write, just a random point in space, okay? So, div of E. Okay, because I wrote this, I don't have to write this, but I want you to remember that it tells me something about the field at a point and a time, and it's true everywhere, okay? So, div of E is equal to what? Remember? And this equation is called Maxwell-Gauss. I will sometimes refer to it like this. Okay, rot of E is equal to and this one is called Maxwell-Faraday.
You're supposed to have also the current in this equation, right?
No.
No?
Div of B.
0.
0. And rot of B. This is where the current is. Who asked about the current? Yarden.
Yes.
This is where it's appearing. Okay. So this is sometimes called Faraday-Thompson. And this is called Maxwell-Ampere. Okay. So now, before okay, the next thing we will do before the break is to make these equations talk. Okay, we will squeeze from them all the meanings that we can. Okay, but before we do this, I want to show you a small... yeah. אחרי הפיזיקה, נראה לי כלום לא...
זה כלום אחרי...
כן. תזכרי את השם. Okay, so I'm now going, you should see this as a small break, okay, before we go into some more intense squeezing of the meaning of these equations. And this is just an overview of what people have to say about the Maxwell equations. אני צריכה...
לא, לא, זה יהיה לבן.
Okay, can we turn the light on? Okay, so let's keep Yarden. What's your name? מה שלך? בואו נשאר בפוקוס עוד קצת. בזום, לא... Okay, so let's see what people said about the Maxwell equation. Carl Sagan, if you heard of him, great. He did a lot of outreach in astronomy. So Maxwell's equations have a greater impact on human history than any 10 presidents. Okay. Ian Stewart, Maxwell equation didn't just change the world, they opened up a new one. Okay. Okay, this is something similar to what I said in the beginning. Okay? And we're being told here, well, first that they are super elegant, this is true, but it's the active force beneath everything we see, hear, feel, smell, and taste. Not sure about the tasting, by the way, but this is basically saying what I tried to say in the beginning, that they describe a very big part of our everyday experience as human beings. Maxwell theories is Maxwell systems of equation by Hertz. Okay, this is by Maxwell himself. Okay, he's saying what he's trying to do. He's actually trying to make a system of equation which will be so universal that they can be understood by everybody regardless of their culture or their background, okay? Okay, this is to give you a sense of the context, okay? And you see, you might be recognizing people here, so of course we have Volta, Ampere, the fathers of electricity, okay? And then Gauss, Faraday, Maxwell. Maxwell is coming after a long list of people. Okay, then Hertz and Einstein. And Einstein is giving credit here to Maxwell. The special theory of relativity owes its origin to Maxwell equations. Okay, it's basically telling us I could have done nothing without the Maxwell equations. And do you know these t-shirts? These nerdy t-shirts of people with the equation, and then it says, and God created light and made light. So there is a funny one about this one, okay? So if you have bought one of these t-shirts with Maxwell equations on the front, you may have to worry about it going out of style. I think it's already out of style, but not about it becoming false. We will go on teaching Maxwellian electrodynamics as long as there are scientists. Okay, it's Steven Weinberg, Nobel Prize, I think. And so, okay, so this was a small parenthesis about the importance of Maxwell equations. And now in the next, okay, so in the next 10 minutes, what we will do is to connect to what we did in the beginning of the lecture. Remember, I defined the conservative flux, conservative field. We gave all these definitions, okay? So now is the time to take these equations and connect them to the definition we used and squeeze from them all the implications. Okay, now it's important to realize that historically it was the opposite. Okay, people discovered all these things about the fields and these equations summarize them. But we are doing the opposite. I'm giving you the equations and I'm asking you, what do they mean about the field? Okay, so let's start with the implications on E. Okay, so E, conservative flux.
But in general.
Who is talking? Yuval. Okay. Yuval is saying not in, I'm asking, is E conservative? Yuval is saying not in general. Does everybody agree?
Not always, only in electrostatics.
Right. Okay, so implications. I'm putting quotes here because, again, historically it was the opposite, okay? On E. So, conservative, not a priori, okay? Why? Because div E is not always 0, okay? We said the conservative flux is when the div conservative flux, not field. I'm asking, this is an important distinction. We talk about conservative flux, conservative field, so I'm asking now about conservative flux, which is the question about the divergence. So, conservative flux, not a priori, okay? Yes, when? So, Itai suggested in the stationary case, not quite, it's in vacuum. Right? In vacuum, the flux of V is conservative. And we can have electromagnetic waves. Exactly, that's okay. Okay, but this is why I insisted on these definitions. It's important to differentiate. So, not a priori. Yes, when? In vacuum. Do you understand why? Because in vacuum, div of V is equal to 0. Okay, and this is the definition of a conservative flux. Makes sense. What's the name of the woman sitting next to Yuval?
Anna.
Anna, it's okay.
Anat.
Yes, Anat, I see you. All good? Yeah. Okay. Okay, so this is one implication. Okay, this reminds you of what? It should remind you of something you did in electricity. The theorem of what? The Gauss theorem. But what should blow your mind here is that in electricity you saw it in the stationary, in the static case. Okay? And this means that the Gauss theorem, so all of this is just implications from one. So Gauss theorem is true in the non-static case. Why should it blow your mind? Because if you remember the way, do you remember how you demonstrated the Gauss theorem? You used the Coulomb force. Okay, you use the fact that E is equal to Q1, Q2 over 4 pi epsilon plus R square, okay? And then you did all kind of surfaces around your charges and you showed the Gauss theorem. But in the non-static case, we cannot write the Coulomb force in the way we write it in the static case. And so this is more general. This thing, the Gauss theorem, is more general than the Coulomb force. And we won't be able to say it about the Ampere theorem. the Ampere theorem, you cannot generalize it to the non-static case, okay, because of this. Okay, so the Gauss theorem is true in the non-static case, and this should indeed blow our mind. Okay, I'm putting here 3 exclamation points. Okay, conservative field, yes or no? Is the field, is E conservative?
In statics.
Okay, so you remember a conservative field is equivalent to say that the rot is 0, right? And so the rot is not 0. A priori, if we have this, it means that in the general case we have induction. What is induction? Is to say that a change in one of the fields is influencing the other field. So in the general case, no, not a priori. Induction. Okay, and when is it conservative? Yes, in static case. Okay? Okay, so this was from 1 and this was from 2. Now let's write the implications on B. Okay, conservative flux, yes or no?
Yes.
Why? Yes, because the divergence is always 0, right? Conservative field, yes or no? Not a priori. When is it? Not a priori. When is it conservative?
Vacuum and also static.
Exactly. Both in vacuum and static situations. Okay, and this is what I told you. When is the Ampere theorem true? Okay, the Ampere law is going to be true only in the static case, right? Because this is actually the Ampere theorem, right? You can relate the rod to the line integral, right? So you see how this is going to give us the Ampere theorem, but it's not going to be possible in the non-static case, which is different from Gauss. Okay, Gauss is generalizable to the non-static case, Ampere is not. So Ampere law only in static case. Okay, now
It's not conservative
okay. Now there are more implications. Okay, it's not bad what we have already, but there are much more that we can take from these equations. So one more implication is the existence of potentials. Okay, the fact that div of B is equal to 0, this relates to your question, Itai, and to the, you remember I told you, this is a parenthesis, I will tell you later, Okay, so the fact that div is equal to 0, div of B is equal to 0, means that we can write B as the curl of another field. We can write B as rot of A, okay? There exists A, such as this is true, okay? And this is defined to a gradient of a function, right? I could add here a gradient. How to say add kedei in English? To? Up to, right. So this is true up to a gradient of a scalar, right? Because the rotational of a grad is 0. Okay, so I could add here a gradient. Okay, now there exists a. Okay, now let's put this in 2. Okay, so if we put this in equation 2, okay, we have that ROT of E is equal to minus dTB, which is equal to minus dt ROT of A, and I can minus ROT of dTA, okay? So writing that ROT of E plus dt of A is equal to 0 for each point in space and time, this is equivalent to writing, if the ROT of something is 0, I can write that this something is a gradient. Right? Because I know that ROT of grad is 0. Okay, so there exists V such as E is equal to minus grad V minus dt of A. Okay? Okay, so these equations, they also contain the very existence of potential. The vector potential A for B and the scalar potential V for E. Okay, and this is, we're used to writing that E is equal to minus grad of V in electrostatics, but you should always remember that when you are not in the static case, we have also another term here. Okay? Okay, and a last implication, and with this we will go to the break, which I think is the most crazy one, is the following. So let's, the last implication is the following. So in vacuum, let's write the equations in vacuum. So in vacuum, I have what? Div of E is equal to what? 0. ROT of E is equal to minus dTB. Div of B is equal to what? 0. And ROT of B is equal to what? Exactly. Okay, so you see that, so ROT is some spatial derivative, right? And dt is the temporal derivative. And what you see here that we have, if you look at these two equations, okay, there is some symmetry here, right? We have a spatial derivative of a field which is linked to the time derivative of another field. And here the spatial derivative of this other field is linked to the temporal derivative of it. Okay, so we have, this is called space-time coupling. Okay, we have a coupling, which means we have a mix of spatial and temporal derivative, which mix two fields together. And what does it remind you? Okay? Waves. This coupling, if you remember from the course about waves, this coupling is an absolute necessity to be able to write wave equations. Okay? Every time you were able to write wave equations, it's because the equations you had in the system made this coupling situation where space and time derivative were mixing. Okay, and so the last implications is exactly, in vacuum we can write here, we have this coupling, and this is exactly what we mean for a wave. Okay, so the last implication, there exist electromagnetic waves in vacuum. Okay, there is light in space. Okay, and in the static case, Okay, if I go static here, this will be 0, this will be 0. No more coupling, no more wave, which is what we expected because a wave is a very non-static thing, right? But it's important to realize this. Maxwell equations, they also contain the very existence of electromagnetic waves, which is very cool, I think. So, for those who want to hear the same things in Hebrew, today's lecture is very similar to the lecture from last year, which was completely in Hebrew. So, and it's on the Moodle. I don't know if you have access to it, but
It's on YouTube as well.
okay. So we're done with the introduction. If we summarize, I reminded you some basic of vector analysis. Then we talked about the basic ingredients of our theory. Then about the Maxwell equations and all the meanings that we can squeeze from them. And now we will start a particular situation, which is stationary systems, which will keep us busy for I think at least 2 lectures. Stationary. I could also call it electrostatics, but we're also going to talk about B, so it's not only E. Okay, so chapter 2. Stationary systems. Okay. Electrostatics. Okay, so let's start by writing the Maxwell equations in this specific case. Maxwell's equations. Okay, so okay, I'm listening. Divergence of B is 0. Divergence of E. Okay, so we'll have the Gauss theorem in the situation that you already met it. Okay. What of B? Mu f is J. Okay, so this is an important point. Stationary system doesn't mean we don't have a movement of charges. Okay, it doesn't mean we don't have currents. It means the currents are constant. Okay? יש זרמים. כן, אבל יש זרמים, גם באלקטרוסטטיקה. יש תנועת, אוקיי? מקורות. פשוט התנועה הזו לא משתנה בזמן. Okay, and rot of E is equal to 0. Okay, so this is the system of Maxwell equations, and this, as usually, is true for each point in time and space. Okay, so here, just to remind ourselves, we will have conservative fields for E. Okay. Okay, and in fact, very often in this in electrostatics, what we are trying to do is basically to deduce the field from the charges. Okay, we know what the sources are, and we are asking what is the field that is being created by these sources. Okay, this is the question that we're asking. Sometimes we want to do the opposite, okay, to go from E to the distribution of charges that generated it. And sometimes we will use the fact that E is conservative and that we can derive a potential to make this task easier. Okay, so when going from here to here, sometimes we will do a detour from V, just because it happens that it sometimes will be easier, okay, to define the questions in terms of potentials and then go through the potentials to solve this question. But today I will focus on this part, okay? Okay, so in the stationary case, we have the privilege of being able to use the Coulomb force, okay? So, force. Okay, so let's assume that we have a source Q and a test particle Q, okay? What is the force that Q will feel at a distance r from small q? So
1 חלקי 4 פאי אפסילון 0 כפול Q, Q, קטנה, גדולה, K בריבוע.
Okay, and we're missing one thing. Yes. R square. Okay, and here I have a vector unity, which directions depends on the values of small q and large q. And there are several ways to write this force in a way that doesn't depend. Okay, so one way is to write, so alternative ways of writing it. Okay, so we can write that the force from Q1 on Q2 is equal to Q1, Q2. You can choose your favorite one. R2. This is if you assume signs for Q. Okay, so if it's negative and positive, it will affect the direction. But the way that I will be using in the rest of the lecture, which is my favorite way of writing it, is the following. First, just as a reminder.
What is the unit that we will use in this course?
The units?
The epsilon UFS or K?
For now we're using MKS, right?
For now, I haven't made any assumption on what we're using in everything that we want.
No, I'm asking what is the unit that we will use in the course?
Depends on the exercise, and if we need you to use specific units, we will ask for it. But everything that we're writing here is units independent.
I'm just asking because there are...
Yeah, it depends on the exercises. It will depend on the exercises.
Okay.
Okay? Okay, so another way of writing this, okay, is the following. And I'm writing this because I will be using this way preferentially. So if Q is located in a point N, okay, then the field that it creates at the point M can be written in the following way. Okay, so this is you need to get used to this way of writing things. The important thing is that here we're not doing any assumption on the direction of any unitary vector, okay? Nm over Nm cube. This is a unitary vector with the correct direction. Okay? So make sure that you understand why this and this are the same, and get used to this way of writing it, because this is the way I will be using a lot. מה? כן, אבל בשביל לקבל את הכוח אני פשוט מכפילה בצ'ארט שמרגיש אותו. אוקיי? Okay, it's fine. I mean, the source, what we have in E is the source. Okay?
זה שלישית למעלה?
כן, זה בשלישית, כי פה יש לי את הוקטור למעלה. אז 1 חלקי זה יוצא ברביעית, ועוד יוניטרי וקטור שהוא בכיוון הנכון. אוקיי? Good. So, can I erase this? This is just a reminder. Okay, so let's write an example. So 2 is going to be okay. So this all should remind you things that you've done. Let's assume that I have a charge here, Q, and an identical charge here, and I'm not assuming anything about their sign. Okay, I'm just assuming that they are identical. Okay, and I have a point M here. And okay, so here it's d over 2, d over 2, and here I have z. Okay, so and here I have R1, R2. Okay, so I will define 2 small unitary vectors that will help me for the system. Okay, so I can write that R1 is equal to d over 2ex plus z ez, and R2 is going to be minus d over 2ex plus z ez. Okay, and they are going to have the same length. Okay, which is d over 2 square plus z square. Okay, and I can write that E at the point M is basic. I'm going to use the superposition principle here and sum the contribution for each of the charges. And what I will get here is 2qz ez. You can double check that you're getting this. This is very basic stuff that should remind you of things that you've done. Plus z square. Okay? And what you see here is that when z is much larger than d, this is equivalent to just one charge with a value of 2q located at a distance z of n. Okay? If you take a z to if you neglect this part. Okay? So this was a very simple example which should remind you of the general expression, general formula for E, for the field. Okay, so in the general discrete case, okay, EM is going to be the sum. Okay, if we have many charges which are located in many points Ni, okay, with an index, then E of M is going to be the sum of Qi Nim over 4 pi epsilon square Nim cubed. Okay? And when I have a continuum, okay, I'm going to have something similar, just with an integral, and of course I can do this integral on a volume, a surface, a tile, okay, it depends on your problem, but on a volume I can write the following. Rho n, n 4 pi epsilon 0 n cube d tau. Okay? this is a very important equation. Okay, that links, so it links rho and E. And the integral here is on the ends. Okay? I could put any other letter here, but it's important to realize that the integral d tau it's on n. Okay? Okay, and I'm going to give you an example to do at home, which is very similar. An example as homework. Okay, and it's the following. Let's assume I have a tile. Okay, with a linear density lambda of charge. Density. Okay, and here I have a point M, 0, and you can define the exact same two vectors. And it's not infinite, the length of it is L. Okay, and we were asking what is the value of the field at the point M. Okay, so I'm going to give you the solution. I'm going to give you the solution and an important integral formula that you need to solve it, and just make sure that you get the same result. Okay, so solution is the following. I think they are also doing it in the Griffiths. So you will get that E of M is equal to 2 lambda L 4 pi epsilon Z Z square plus S square EX. Okay, and you will need to use the following integral formula, which dx, which is equal to x over a square 1 over square root of a square plus x square plus a constant. Okay, and here too you see that if z goes to infinity, you're getting the equivalent of one charge with value 2 lambda L, okay, which is what we would expect. Okay, so in principle we could stop here, right? I told you that the whole point of electrostatics is to link between a distribution of charge and the field that it generates, and we have here this formula, so we could in principle say that we're done. But the problem is that very often this integral is extremely hard to solve, okay? And so we are using all kinds of strategies to try to avoid solving this formula. And some would say that the entire electrostatic field is about finding alternative solutions rather than solving this integral. Okay? Whether it's by using the Poisson equation and going through in the Griffith they write that electrostatics is basically solving the Poisson equations, okay? By going through the potential. But the point here is that all the rest is about strategies to avoid this integral. And I'm going to talk about one of these strategies, which is the Gauss theorem. Okay, and I will not rederive it.
If you use this theorem for the tile, you need to add the delta function for the density, right?
You don't. I don't see any reason really to use this for the tile.
If you want.
Yes, you could.
You need to add the delta functions. Maybe theta also. If you want to just
you have to really want to use the Gauss theorem in this case, but you can.
Okay.
I don't think you need that in the continuous case. You're not using delta functions
for the density. For the charge density, I can present him with delta functions for the charge.
Yes, but you can try as an exercise to solve it with Gauss, but I'm not sure how we think about it. Okay, can I erase this? Okay, so one of these strategies is the Gauss theorem, which I will prefer to call the Maxwell-Gauss equation. Okay, and so again, I'm assuming that you know how to use it, that you know it. In the first years that I gave this course, I assumed this, and then the first exercise in the exam was to use it, and half of the people didn't remember how to use it. So remind yourself how to use it. Do the homework exercises. We're going to help you remember how to use it. It's an important thing, and we're assuming that you know how to use it. Okay? But now I will try to give you some hopefully added values on what you already know about it, which is just strictly how to use it. Okay? So let's start with the theorem itself. Okay? It's important to realize that the Gauss theorem is always true, okay? But it's not always useful. You can always write the Maxwell-Gauss equation, but it will not always help you to solve to avoid this integral. Okay, just in very specific cases. But let's write it. Okay, so I have that divergence of E is equal to rho over epsilon 0. Okay, and because I can use the divergence theorem, then I can write the following. Okay. No, this is just integrating this and this. Okay, and this is equal to q int. Int here is, I will write it as n. Okay, n is enclosed in the volume. Okay, it rings some bells. It reminds you of things, right? Okay. So this is just writing. This is by the very definition of rho. Okay, and because of the divergence theorem, I can write that this is equal to what? To the flux of E through S. Okay? And so, if I summarize, the Gauss theorem is basically writing that E ds is equal to Q enclosed. Okay, the integral, the flux of E through a closed surface is equal to the contained enclosed charge divided by epsilon 0. And this is always true, not always useful.
מתי זה כן שימושי?
בדיוק נדבר על זה עכשיו. Okay, so when is it going to be useful? I remind you that what I'm trying to do is to avoid solving integrals. I don't like integrals, so I want to be able to take E outside of the integral. When will this be possible?
For high symmetry.
In some very specific cases where the symmetry of the problem is allowing me to take it out of the surface. Either because it's parallel to the surface and then this becomes 0, or it's perpendicular to the surface, but this will not be enough. I will need it to be both perpendicular and constant over the surface, and then I can take it out and avoid the integral. Okay? So, and this, as a reminder, this tells you how to choose your Gauss surfaces, okay? You need to choose surfaces that are either parallel or perpendicular to E, and where it's perpendicular, you want it to be constant, etc., etc. Okay? Now, I want to, again, I'm not going to demonstrate the Gauss theorem in the static case. what I will try to do is remind you of the intuition of what it's telling us. Okay, what is the deep meaning of the Gauss theorem? And I will also share with you a question that I was asked in the first year, which is a subtlety of the Gauss theorem, which we don't always realize, but it's also very important. Okay, so and this intuition is also given in a very nice way in the Griffiths. Okay, so intuitions. Okay, so to get an intuition of what the Gauss theorem really means, it's very useful to use the tool of feed lines. Okay, because feed lines, by counting field lines, I'm actually measuring the field in a sense. Okay, so we're going to use this in two cases. So two cases. In case one, I have two opposite charges. And in case two, I have two identical charges. Okay, now let's look at the field lines in each of these cases. Okay, so I remind you, do you remember how they are oriented?
Going outside of the positive and...
Yes. Okay, so it's going out from the positive and, oops, like this, and going towards the negative, okay? And here, there are also some very nice simulations that you can find on the internet where you can decide how many charges you want and it draws the field lines for you, which is very cool and also something that our ancestors didn't have. Okay, so now in order to quantify the field, I'm going to draw some boxes around these charges. Okay, why? Because eventually I want to say something about the flux of the field, and saying something about the flux of the field is basically counting what is going in and out of a box that is around the charge. Okay, so I'm going to, sorry. Okay, so I'm going to draw two boxes. Okay. Okay, so in order to count what's going in and what's going out, I can simply count field lines that are going through the box. Okay, so in the first case, all of these lines are staying inside the box, right? And these lines, the same amount, I only drew one here, but you can see that the same amount that's entering is also going out, okay? And so this means that here, what's going in is going out, okay? So the flux is 0. ds is 0. You agree? And here, this is not true anymore, right? Here, the things are going out. Nothing is going in. Okay, so in this case, I have a net movement of field lines outside of the box, and I can write this.
רגע, אבל אם יוצא החוצה, זה חיובי?
כן. כי אפשר גם, זה קונבנציה, כאילו כמו שהחלטנו שהם יוצאים מה... כן. לא, אבל החלק, the part of the convention here is to decide that the field lines are going outside of positive charges, okay? But yeah, I mean the S is always oriented outside, so if you orient the field lines like this will be true, okay? And this is exactly the intuition, okay, which tells us that the flux. Now, okay, what else is zero in this case? The sum of the charges, right? And what else is positive here? The sum of the charges. Okay, so the intuition here is to say the following, that the flux through the box is a measure of the amount of charges that is contained within the box. Okay, this is Gauss theorem. But it's not enough. It's not only it's a measure, it's also proportional. Okay, this is not contained in what I've done here, but this you know, okay? Because of this, you know that it's proportional. If I multiply the amount of charges by 2, the flux will be multiplied by 2. If I divide it by 2, it will divide, okay? It could be some other links, right? It could be square root, it could be all kinds of things, but no. Gauss theorem is telling us that there is a proportionality and that the measure, that the flux through the box is giving us a measurement, okay, it's proportional to the amount of charges that are contained inside the box. Now, this part might be intuitive to you. I don't know if it's intuitive to you. But there is another part which is really not intuitive, which I will now try to, this is a subtlety of the Gauss theorem, which I will try to give you an example of. What happens if I move the charges now inside the box? The field will change in space, everywhere in space, right? If I take these two boxes, I keep the charges in the box, I move the charges. The field in every point in space and specifically on the boundaries of the box will change, right? But the flux will stay the same. Now this, to me, is really not intuitive. I think it's really not intuitive. It's like a subtlety of the Gauss theorem, and it's an important one. Okay, there are many different fields that can lead to the same flux. Okay, but the charges here, they don't define the field on the boundaries of the box, but they do define the flux of the field on the boundaries of the box. Do you understand the difference?
How can you explain it?
This is what Gauss theorem is telling us. And like you don't know, you need to not do the one more step, which consists of saying, okay, the charges, they define the value of the field on the boundary of the box. This is an additional step that we cannot do. They only define the flux. And so in the first year, a student came to me and asked me, okay, I have a sphere. I have a sphere with charges in it, okay? And that's it. It defines, so I apply Gauss theorem. It gives me the field everywhere in space, right? I use this. It's symmetrical. I can use the Gauss theorem. I can get the field. Now my field is defined by these few charges inside the sphere, everywhere in space, everywhere in החלל, okay? And it also defines all the charges in the universe, remember, because the fields also influence the charges. And even if I add charges outside of the sphere, my field is already defined, right? So where is the problem in this thinking?
The field is not constant.
Exactly. If you add, the moment you add charges outside of your surface, the field has changed everywhere in space and also on the boundaries of the surface. But the one thing that hasn't changed is the flux of the field, okay? And this is a subtlety, you should think about it, make sure you understand the difference, and you can try to use these simulations online, where you can define a surface, you can add a third charge and C, the field is changing, the flux is not. Okay, so this is a very important point. Now, in the remaining 6 minutes, I will say a few words about symmetries. Okay, so usually, I know that the way we study it in Israel is we consider symmetries and invariances as being the same way, the same thing. Okay, we say the symmetry of the problems leads to E not depending on more than one coordinate and the direction. So the way I learned it, there was a very clear separation between invariance, which is which variables your field depends on, and the symmetry, which gives you the direction of the field. It might or might not help you, okay? I will just give you a few elements to food for thought that you could use. Okay, so okay, the key here is that to use Gauss theorem, we will be using the fact that the symmetries on the charges are translating into symmetries on the field. Right? So if your charge is spherically symmetric, you will be able to say something similar on the field. Okay, so let's give the statement. So if we have a symmetry plane pi, I call it pi, okay, and here I have 2 points which are geometrically symmetric. Okay, in a geometrical sense. Okay, so this distance is the same as here, and okay, and so if by definition, if pi is a symmetry plane, it means that rho at point P is equal to rho at point P dot. Okay. And now, if pi dot is an anti-symmetry plane, okay, so pi is anti-symmetry plane, it means that rho at point P is equal to minus rho at point P square, P dot, okay? And the way we are using it in exercises is that if I have a point M here, okay, in each point which is contained in a symmetry plane pi, okay, E is contained in pi, okay, and in each point containing an anti-symmetry plane, this E is perpendicular to pi square, okay? So this is another way to write the one sentence that you write at the beginning of exercises, which say by symmetry, okay? So I'll give you an example. If I have a distribution of charges which is spherically symmetric, okay? We always say that E is radial. Why E is radial? Because all the planes that contain the center are symmetry planes, okay? So E needs to be contained in all of these planes. And so there is no other ways than E being radial. Make sense? So if we have a spherically symmetric distribution, Okay, all the planes that goes through the center, all of them, they need to contain E because of this, and the only way to do this is the radial field. Okay, I might get back to this next time because I feel that I've slightly lost you here. We will stop here because there will be some exercises to refresh the Gauss theorem. I wanted to give you a small example, but you will get it either in the tutorial or the exercises, so we can stop here for this time. I think we're right on time, so have a good week.
זהו, אז שווה לבדוק.
עכשיו יש לי תרגול, אבל כאילו אני מניח שעוד